Chapter 18, Algorithms. What is an algorithm? Algorithms are studied for efficiency, so this is something that I'm going to be referring to as I go through the lesson, and I'd like that is referred to as a big O notation. Um, Please read on your own all the items that are listed there, and as I mentioned in class, I'm just going to kind of highlight the things that I think are super important or that I want you to know will be covered on the quiz. The steps for writing algorithms. The 4 steps for writing an algorithm are you definitely should know how to plan your code, write your code, which is the actual code itself, test the code, and also code that does not run as intended is often called something called a semantic error. So that's important. So semantic errors are caused by mistakes in your logic, and semantics errors may not be detected without testing. All right, more about algorithms. These next few definitions are going to show up on your quiz, so make sure you review these a few times. If an algorithm runs in a reasonable time, it means the number of steps it takes is less than or equal to a polynomial function based on the size of the input. It is faster than an exponential function. So for example, if you have an exponential function 2 to the x, the variable is in the power. An example of a polynomial function is x squared. The variable is raised to a power. Algorithms that require an unreasonable amount of time may solve the problem correctly, but they may not be useful because they take too long to execute. The algorithm may have used a heuristic to improve its speed. So a heuristic is a set of rules used to get close to a solution. A heuristic makes sense if an appropriate solution is good enough. Heuristics can be applied to solve problems faster. Not every problem can be solved using an algorithm. Problems that cannot be solved with an algorithm are called unsolvable. Problems that cannot be solved in reasonable time are called intractable. Problems that have a yes or no answer for all the inputs are called decidable. Problems that do not have a yes or no answer for all inputs are called undecidable. Some instances of undecidable problems may have a solution. Often these instances are limited versions of the problem itself. So these last 2 pages are pretty important. Algorithms are described using math patterns and denoted using, well, here's that word again, big O notation. So big O notation means on the order of. It's a shortened way to describe the efficiency of an algorithm. Efficiency of an algorithm includes both the following: the memory usage and the execution time. Efficiency is determined using math reasoning about the algorithm. Efficiency is tested by running the algorithm with different inputs. Some algorithms are described by their purpose. For example, encryption algorithms help keep data transmission secure. Optimization algorithms give the best solution from a list of choices. When you're searching for something in a list of data, that's different than sorting elements where you're putting things into particular order. Be able to do the following with algorithms, and I want to highlight the second bullet point. Designing software means moving through these 3 phases, words, pseudocode, and code, in the following 2 ways. You can do that incrementally. When a part of your design is completed, it is put into a larger project, or iteratively, revisiting code after it's completed to revise and improve a program. So in the first case, you do a little bit, you do it all correctly, and you add on, or you try something, you test it, you go back, you revise, and then you continue on. So you should do the next example. Seems to be pretty reasonable based on what I have here in my notes. Moving on to the next page, some other things that I thought were important. So there's going to be questions about all different kinds of algorithms, and it's important that you go through this code and you understand how it works. So you should be able to recognize and evaluate a few standard algorithms. The first one being find the minimum in a list. So finding the minimum involves two data structures, a list and a variable to hold or keep track of the minimum when it's found, and also a loop to access each element in the list. So here is pseudocode for that. So basically what you do is here's your variable for the minimum, and you just grab one of the elements in the list. Then you have a for loop that's going to go through every item in the list. As you march through the list, if the first item, or if any of the items is less than the minimum, which has been stored in the variable, you then reset the minimum to that item. If it's not, then you just leave the minimum alone. But you march through every item in the list, and then when you're all done, you return the minimum. So maximum works very similarly, only this time the big difference is in this condition. So instead of checking to see if it's less than, you're checking to see if the item in the list is bigger than the maximum. And if it is, then you reset the maximum to that item. And then when you're all done, you return the maximum. Other standard algorithms include finding the sum of numbers. So when you do that, you're going to use two data structures, a list and a variable to hold the sum, and then a loop to go through every item in the list. On the next page, once again, is some pseudocode. Here's your sum. Here's your loop, looping through every item in the list. And every time you encounter one of the items in the list, you add it to sum. And when you're all done, you return sum. The other standard algorithm is finding the average of a set of numbers. This involves three data structures, a list and two variables. First, to hold the sum, the first variable holds the sum, and then the other variable holds the average. And once again, you're going to need a loop. So I have a variable for average and sum, and notice how I'm setting them both to 0. I have my for loop that's going through every item in the list and adding every item to sum, just like in the last algorithm. Now, this last bit of code is where the average is actually calculated. You say, as long as the length of the list has more than one thing in it, you calculate the average, which is equal to the sum divided by how many items are in the list. And then you return that average. So I think those things are very straightforward, and I think we can move on from there. Now, other algorithms are searching for an element, often called the target in the list. So finding an element in a list involves two data structures, a list and a variable to hold the location it is found in, and then a loop to go through the list. There are two primary algorithms for searching. The first is a linear search. This search starts at the first item in the list and keeps checking till the very end of the list. So in a worst case, you're going through every item in the list. The second one is called a binary search. In a binary search, the items in the list are in a sorted order. You establish a middle, and then for the item you're looking for, the target is compared against the middle. If the item is in the upper half of the list, the bottom half of the list is thrown out essentially. So let's look at that on paper. So if I have a list that contains 5 things, the integers 1, 2, 3, 4, and 5, and this say my target is 4, I establish a low a middle, and a high. I'm comparing my target with the middle. If the target is bigger than the middle, then this becomes my new array, and I throw out the first half. I then only work with 3, 4, and 5. I work with essentially a smaller array. I find the middle again, and I compare my target with the middle. If it's equal, obviously I'm done, and we would return this location. But if it's not, excuse me, this should be 0, 1, 2, 3, 4. This would be 2, 3, 4. If I'm not, I would throw away whatever part of the array it didn't belong in. As we move on,